What's today? The 18th. Ay, ay, ay. Blue.
In history, there's no. Oh, you said any time. You said any time in the middle. Yeah. But I did.
So we have to approach these a little bit differently, I think. Maybe we don't. Maybe we can approach these the exact same way that we have been. Let me try it and see if it works the way we've been learning them and see if we can work through them that way. I think we probably can. There's just going to be some funkier answers at the end, but I think we can get through this the same way. So I have 4 examples. Let's get to the first one. So we have the absolute value of x plus 3 is greater than or equal to 2x minus 5. And yeah, I'm pretty sure that we can do this the same. Yeah, good news for you guys. So I think what we're going to do is just try to find the boundaries first. There are going to be none of these where we have to get the absolute value by itself. I spared us that step. So in none of the examples or any of the homework problems will you have to worry about that. So the problem itself is already the crossroads, the part where we split it. So, and remember with these, we don't just look at them and make snap judgments like we have in the past, right? Like sometimes if it said like just greater than -5, then I could be like, ooh, all real numbers or something like that. But here, because there's a variable, and this is where it changed also with equations, when there's a variable on the right-hand side, we can't look and just make a snap judgment because the variable makes anything possible. So we have to consider both scenarios. So to find the boundary on the left, we're going to say that x plus 3 can equal 2x minus 5. And to find the boundary on the other side, I don't know, maybe my left and right could wind up being backwards. I'm going to say that x plus 3 could equal what? -2x plus 5, right? And I think this method will work. Honestly, I've never done these problems this way. You'd think I would have in 29 years, but not exactly sure, but I don't see any reason why this method won't continue to work. So let's track down boundaries. So for the equation on the left, we're going to wind up with x equals 8. And you can work through that at your own pace to agree or disagree with that. And then this one, we're going to wind up with x equals, what's that going to be? 3, 2, 2/3. So on the red one, I subtracted the x to the right and then added 5 to get 8. And then on the purple one, I added the 2x to the left and then subtracted the 3 and then divided by 3. So that's how those came to exist. So we're going to draw a number line because it seems to be the method that you guys like to use. So we're going to draw a number line and then we're going to mark our boundaries and then we're going to test regions. So the number line will have 2 boundaries. And sure enough, they were the opposite of what I thought they'd be. But that makes sense because I set them up like a ding dong. So we're going to have our 2/3, the smaller one on the left, and our 8, the larger one on the right. Sound good? So let's test some bound. Oh, let's put some circles on there first. Open or closed? Yeah, they're going to be colored in, right? Because we had the or equal to. So we could color these in. What you're going to start seeing today are, and the reason this lesson exists, I wouldn't even probably be teaching this if it were just more of the same. But what's going to change today is you are not just going to have splitters and squishers. We're going to have sometimes graphs that overlap each other. And so for the first time ever, we might actually wind up seeing graphs that go, both to the right or both to the left. Strange things can start to happen now that there's a variable on the right. So we're just going to patiently, faithfully test the regions. And I just like to call them 1, 2, and 3. You can call them anything you'd like. You don't even have to call them anything. But let's start by testing the region on the left. What's the most sensible number that I could test on the left?
Zero.
Did you say -2? Yeah, that's interesting that you'd say that, but I like 0 a little bit better. So I'm going to go with 0. Seems a little bit maybe less work. So I'm going to take 0 and I'm going to put it up here where these yellow arrows are pointing to. And I'm simply going to see if what I get is a truthful statement, as always, or a false statement. And so if I put 0 in the first little yellow arrow, 0 plus 3 is 3, right? And the absolute value of 3 is 3. So I'm currently sitting here wondering if 3 is greater than or equal to something. And then if you put 0 in the arrow on the right, 2 times 0 is 0, and 0 minus 5 is -5. And is 3 greater than or equal to -5? It is. So at this point in time, what we're going to do is maybe you can mark it with whatever you want to, maybe put a little happy face over here or something like that, just to remind yourself that, hey, I tested region 1 and he's good to go. But again, you cannot today assume now that and that's those of you guys that have been working hard and practicing and getting all your problems done, you know that in the past, this would have implied that we for sure just have a common splitter, right? It would be done. We'd go shade the other side, leave the middle out, and that's that. But we're not going to go down that road. Because like I said, weird things can happen. So let's also test region 2. What's a good number for region 2? 3 works wonderful. So if we test 3, because that falls right smack in the middle of, it's nice and between 2/3 and 8, we're going to go back up to the beginning. And again, we're going to test, we're going to put where the little yellow arrows are, we're going to put the number 3. What's 3 plus 3? It is. And the absolute value of 6 is 6. So we're just kind of sitting here waiting. 6 is greater than or equal to, well, what? And so if you put 3 in place of the yellow arrow, 2 times 3 is 6, and 6 minus 5 is 1. And 6 is in fact greater than or equal to 1. So oddly enough, region 2 also gets a happy face. You see that this is the first time ever that this has happened. These two have always been exclusive in the past. And all the 20, 30, 40 problems we've worked on and worked so hard on, if the outside one works, the middle one never does. But here now we find ourselves in quite an odd situation where now they both work. And let's test region 3. If region 3 works, what will we say? All real numbers. And if it doesn't, then that's a different conversation. So let's test region 3. What's a good number to test for region 3? 10's perfect. It's kind of, I think, what most people would gravitate to, just a nice roundy kind of number that's clearly in the region. So let's test 10. And again, put 10 where the little yellow arrows are. What's 10 plus 3? 13, and his absolute value is also 13. So we have 13, and we're just kind of in a holding pattern here. And so we have 2 times 10 is 20, and 20 minus 5 is 15. And 13 is not greater than or equal to 15, correct? So we can agree that this region is no good, correct? So when we describe this now, we have to not think of it as, one of the ones that we're used to. We have to think just look at it. Don't be a ding dong. Look at it and just ask yourself, okay, let's take a good objective look at this and just ask ourselves, what is shaded? Well, we know that everything in this region is shaded, but we also know that everything in this region is shaded, which gives us a solution set like we've never seen before. And it's just one big region. It happens to be sort of the, how do I say this? Like the blending of two regions. And the one thing that makes this work is that in between these is the word or. This greater than sign implies or. And so because either one of those greater than imply, you should write this down. I'm going to have you write this down right now. If you see a greater than, of course, or a greater than or equal to, it's going to be a situation that is or. If you see a less than or a less than or equal to, then that situation implies an and. And because either of the shadings can be true, the word or is very powerful here. It says that you can be in region 2 or you can be in region 1. And for that reason, both regions work just fine. Think of it like if I said, give me a number that's either even or a multiple of 6. You could give me either. Like if you gave me, either category, well, I should say, let's say I asked you for a number that's even or a multiple of 5, right? You could give me either category of number and I would call what you did a winner. But if I changed my wording to and, then you'd have to be more particular, right? So like if I said, I need a number that's even or, and I'm just going completely off topic here just to try to make a point. If you're going to get lost, it'll be right about here. If this was my requirement, I sent you home with an assignment and I said, I need you to come back tomorrow with either an even number or a multiple of 5. If you brought me back the number 15, would you win? Yes, you would. And you'd say, well, hold on a second, but 15's not even. But the word or means that you can be in either category. And 15 is, in fact, a multiple of 5. So for that reason, 15 would work. If I changed the wording and I said, I want you to come back tomorrow, your homework is to bring me a number that is both even and a multiple of 5. Would 15 work? No. The word and implies that you have to be in two places at the same time. And 15, yay, may be a multiple of 5, but he is not even. Could you give me an example of a number that would work? 10, 20. Those are all wonderful answers because they are both even and a multiple of 5. So as you go through this assignment today, as you saw, the process of what we're doing, like the finding the boundaries, the testing the regions, it's all very ho-hum, it's 10th verse, the same as the first. It's just that as you see throughout the problems we're going to do, we have to be smarter today about asking ourselves, is it or is it and? And if it's or, it's almost like just open season, do your thing. If it's and, we've got to be very much more particular. Okay. So the answer to this problem, and again, sorry for the sidetrack, but I hope that makes sense. The difference between or and is really huge. So if we look at the graph that we have and we go to write the solution out, we only need one region. I don't need to I don't need to write this two different ways. How could you generally just describe this entire solution region for me? X is less than or equal to 8. Done. That's all I have to say. And we're not used to answers like that, but that one statement says everything that we need to say. We're trying to say that every number 8 or less works, and we can see it with our own eyes. We found the boundaries, tested the points, done. Okay. Let's do another one. The absolute value of negative 3x plus 1 is less than x plus 4. So again, no prep work necessary. We're just right to the point where we're searching for boundaries. So one of my boundaries can be obtained by just essentially writing an identical copy of the problem with an equal sign and no absolute values. And then my other boundary can be obtained by keeping the negative 3x plus 1 the same and hitting the right side with a full switch. What's that going to be on the right? Negative x minus 4. And that's the double switch on the right-hand side. So, basic algebra hopefully is not going to hinder us here. What's the solution to the red equation? We'll go a little bit slower. So last ones I think were pretty simple. I'm going to add the 3x across over here, giving me 4x. And then I'm going to subtract the 4 across to the left, giving me negative 3. So now I would ask you, what does x equal? Negative 3 over 4. And I will warn you that it's really easy to say those upside down. I see it all the time because, I think if I were more of a stickler and required you to show your work, like we did back when I first met you at the start of Algebra 1, then you would never say -4/3 because you could literally see yourself dividing by 4. So if you're someone who would have been inclined to say 4/3, maybe you're someone who might want to, just for safety reasons, show that last little baby division step to make sure you get everybody where they belong. So one of our boundaries is at -3/4. How about this purple equation? Again, I'm sorry, go ahead. That's what I'm seeing is 5/2, right? So if I pull the 3x across to the right, by adding it, I get 2x's. And then if I add the 4 back across, 1 plus 4 is 5. And I believe then that x must equal 2.5 or 5/2, whatever you want to call that. So again, let's go to the number line. And let's at least set up our boundaries, find our regions, and then do some, I hope, pretty basic math to test the 3 different regions. And you'll always have 3 regions, right? 2 boundaries always logically will create 3 regions. So -3/4 is going to go on the left, and +5/2 is going to go on the right. So let's test regions. Region 1, region 2, region 3. Can I have a number in region 1? -1's perfect. -1's a little more negative than -3/4, and it's a pretty friendly number, but it's obviously to the left of -3/4. I mean, you can put your boundaries on if you want to right now, by the way. So if you wanted to put your boundary circles on, you're welcome to do that as we go. Okay. So -1 is certainly a good number to test for region 1. So we're going to go up here, as always, to where these little arrows are pointing, and we're going to change them into -1s. So inside the absolute value, what's -3 times -1? +3 plus 1 is 4, and the absolute value of 4 is, of course, 4. So we're sitting here waiting. 4 is less than, don't know yet. But if we put -1 where x is, what is -1 plus 4? 3. Is 4 less than 3? It is not. So region number 1 is no bueno. Cross that one out. Okay. Let's take a look at region 2. What's the obvious candidate for region 2? 0. Anytime you give me a negative and a positive boundary, 100% of the time, I'm going to use 0. Because 0 is the super easiest number in all of math. So if I put 0 in place of those little yellow arrows, -3 times 0 is 0. 0 plus 1 is 1. The absolute value of 1 is 1. So 1 is less than. We're waiting. And then we put 0 in for x. What's 0 plus 4? Is 1 less than 4? It is. And so I am going to put a little happy face or any notation you want. The happy face is pretty dorky, but if there's any sort of notation that you wanted to use just to track your regions, you pick. It doesn't matter. Green check marks, X's, yeses, nos, whatever you're going to do to keep track as you go. And then let's test region 3. What's a good number for region 3? 7. Random, but wonderful. I love 7. So let's go up here where the yellow arrows are, and let's change them both into 7s. -3 times 7 is -21 plus 1, the absolute value of which is 20. So we're looking and waiting, is 20 less than something? And then if we test 7 on the right, 7 plus 4 is 11. Is 20 less than 11? Nope. So this one came out really, really simple. And so this one is obviously a lie as well. And so this is a standard response like we're used to. Sometimes you'll get the old familiars. And so this graph is exactly what you're accustomed to seeing. It's going to actually just wind up being a squisher. Who'd have thunk? Okay. And so to write this one, what would my solution say? Perfect. Okay, I want to do a couple more examples with you, and then I want to show you some funky sorts of other scenarios. It's hard to write a lesson like this and not put you to sleep and account for every possible scenario. So I do want to go through just some, not entire problems, but just some potential endings that we might see. But I do want to do 2 more full problems with you. So the next one is the absolute value of 2x minus 5 is greater than -2x plus 7. So we're going to find our boundaries. And for the boundary on the left, we have 2x minus 5 equals negative 2x plus 7. And then for the boundary on the right, we're going to have 2x minus 5 equals 2x minus 7. Correct. Okay. So this is an interesting scenario, and I think I'm probably going to back us into a nasty position here where we may have to do this problem a different way. But we'll see. Let's look at the red equation. What's going to be the solution for the red equation? X equals 3. Good math. Yep. And the one on the right? This one has no solution. Yeah, it had no solution at all. There's not a 0 here at all. Yeah, when you subtract 2x from both sides, what happens is the x's go away. And when you have an equation like this where there's no x's left, you just have to look at the numbers that are left. And because negative 5 can never in a million years actually equal negative 7, then this equation is unsolvable. So this one produces absolutely nothing. Got it? Okay. So what we have now is a point. So how many regions are we going to create? Just 2. Yeah, if you take a number line and just only throw one boundary on it, it's just going to break the number line into 2. So we're not accustomed to that. We're accustomed to seeing 3 different regions. Here we only have 2. And because this says is greater than, we're going to leave 3 hollow. So this is an open circle, which means that 3 is not a part of the number line. Now, what we're expecting to see here is a situation where we're either going to shade, either the left or the right. That's kind of what we're used to. So let's find a point on region 1 first. What's a good number in region 1? Again, I would pick 0. Mara, you seem to want to work harder than the rest of us. So I'm going to take 0 because 0 is the easiest for me. So if I put 0 in place of the yellow arrow x's, what is 2 times 0? 0 minus 5. Absolute value of that is, so we're just waiting to see, is 5 greater than something. If you put a 0 in the one on the right, what is negative 2 times 0? 0. 0 plus 7 is. And is 5 greater than 7? It is not. Therefore, region 1 can have a little red X or something like that. You can mark it on the line or whatever you want to do. All right, let's go test region 2. Our assumption is that something in region 2 is probably going to work and that we're going to get just a regular old algebra 1-y kind of looking graph. So let's go test. What's a good point for region 2? Say it again. No. 4 would work. 5 would work. 3.1 would work. Anything to the right of 3. Did you say 4? Let's do 4. So go up where the little yellow arrows are and change it into 4s. And what is 2 times 4? 8 minus 5. And the absolute value of that is 3. And then again, we're just in a weighting pattern here. So 2 times, what did we say? 4. What's negative 2 times 4? Negative 8 plus 7 is negative 1. Is 3 greater than negative 1? It is. And so this region turns out to be true. And so we would just shade this region. Okay. And by the way, sometimes both regions will fail. Okay. And if that had happened, if both regions had not worked, what would we say? No solution, right? We wouldn't shade anything. So in this case, our solution set is quite simply any x that is greater than 3 will work. Okay. Good. All right, let's look at one more. We have the absolute value of x minus 3 is less than negative 1/3 of x minus 5. Let's go find some boundaries. The one on the left will be, oh, I shouldn't keep saying it like this. One of the boundaries will be found here. And then the other boundary will be found where? X minus 3. Nice job. 1/3 of x plus 5. You guys are good at hitting that right side with the double switch. Good job. So this is a good time for fraction killing, right? I know that, again, we're a little rusty, but I did have you do this on a recent assignment, or something, but it did. Was it on the test? It was on the test. You're right. So what we're going to do is let's just multiply by 3. And again, anyone who says that this is a wasted step, they're not wrong. Like you're not getting any closer to solving it, but I would just tell them it might not get me closer, but it sure makes my life a lot easier. So if I multiply by 3, what do I get on the red equation? 3x minus 9 equals, no, just negative 1x because the 3's cancel, minus 15. Got that? So remember those 3's canceling kind of makes that multiplication really never happen there. And solving the red equation, we wind up with 4x's over here. What's negative 15 plus 9? Thank you. And then if we divide both sides by 4, we find one of our boundaries is at negative 3 over 2. Negative 6/4, of course, reduces to that. All right, let's take a look at Mr. Purple. Again, if we multiply by 3, it's essentially the same exact process, just the signs are a little different. So we wind up with 3x minus 9 equals what? X plus 15. So again, we just manipulate, we move stuff around, move the X over here, you get 2 of those bad boys. Add the 9 over here, you get 24, divide by 2, and you get, well, 12. So we're going to get 3 regions this time, and we're going to go test them and see what happens. So we're going to make a number line. Oopsie, wrong color. Like this. And we're going to go to negative 3 over 2 and 12. And if you want to put in some hollow circles. Regions 1, 2, 3. Can I have a point in region 1? Yeah, it's got to be more negative than negative 1.5. So negative 2 would work fine. Negative 2 is going to be over here somewhere. So negative 2 is a good tester. Anything less than negative 1.5 would work. You could do negative 50 if you were feeling crazy, but negative 2 is pretty slick and quick. So let's head up here and put negative 2 right there. Oh, you know what? Why don't we, to make our lives easier, why don't we pick a multiple of 3? You guys see why? It's going to be easier to do this second yellow arrow if we pick a number that can hook out with the 3. So why don't we do negative 3? Negative 3 will make our lives a little easier. And then we don't have to use a calculator and all that nonsense. So negative 3 minus 3 is negative 6, the absolute value of which is 6. So we have 6 is less than, and what's negative 1/3 times negative 3? Positive 1. And 1 minus 5 is negative 4, and 6 is certainly not less than negative 4. No way, no how. So region 1 is no bueno. Good. And then for region 2, what's the sensible choice? 0 is always a good choice. And so we're going to change these into zeros. And it looks like we get 0 minus 3, negative 3. Absolute value is 3 is less than, and then this one is negative 5. Is 3 less than negative 5? Absolutely not. So it looks like region 2 can also get a ka-chunk, ka-chunk. Now let's go test region 3. What's a good choice for region 3? 15 is fine. Sure. It's a good one. It's a nice multiple of 3. I appreciate that. So we're going to pick 15. And then inside the absolute value, what is 15 minus 3? Absolute value of 12 is. So we're waiting to see 12 is less than what? What's negative 1/3 times 15 right here? Negative 5. And what's negative 5 minus 5? Is 12 less than negative 10? It is not. So what we just found is a nice visual example of one that has no solution. Right? It's an odd sort of scenario, but sometimes that happens. If you just test everything and nothing works, then that's the math God's telling us that it didn't happen in. So good. I think I'm gonna just give you a couple different scenarios. I said I would, so just give me a couple minutes and then we'll be done. So let's say that we were just at the end. So that's it for the formal examples. I just want to show you now some different things that can happen. So let's say that we were doing a problem, and it doesn't matter what the boundaries are. So let's say that it was a less than problem. Remember that less than means and, right? And you got a graph that went this way. So let's say you tested region 1 and it worked. And then you tested region 3 and it worked. And let me put some numbers on here just so that you have something there. So like this, whatever. But again, remember that the original problem said and less than. What would the solution be? It can happen. Nope. What would the solution be? Nope. What would the solution be? I don't know. Just like the number 0? No. How about this? I'll give anyone in this room right now, I'd say like $20. Ready? $20. If you can find me a number that is here and here. Ready, go. No, just one number. One number. Just one number. I want you to find me one number that could be in the left arrow and the right arrow at the same time. Correct. There is nothing that this could work for. So this is where it really comes back to something I said 20 minutes ago about the difference between and or. If this was an or problem, then you would just write x is less than -4 or x is greater than, like, easy peasy. There's nothing to it. But as soon as we have this situation where it says is less than, and it implies the word and, you literally cannot be in this one and this one at the same time. So if that were to happen, even though I have a graph that feels like it contradicts this, I would be forced to say no solution. Got it? And then the only other, did that make any sense at all, by the way? Okay. The only other situation that can arise is a situation like this. I shouldn't say the only other situation, but another common one that can happen is, oh, snapdragons. Get on there. You make a straight line, you knucklehead. There you go. Mr. Artwork over here. So let's just say we had like -2 and 5. And we had a graph that had like this, and this region worked. And then we had a graph like this, and this region worked. And let's say that it was another and problem. So at the beginning of this problem, let's just say that there was a less than in the problem. Remember, a less than implies that both things have to be true. So if you get this one, again, good job. That last one stumped you. How about this one? If I tell you that both of those have to be true, what would the solution set be? Nope. The thing is, if I pick a number, so if I picked a number like right there, and I'll just pick one like 3. 3's in there somewhere, right? Is 3 greater than -2? Yeah. Is it also greater than 5? The word and carries a lot of weight. The word and means both things have to be true. So I'll ask you again, what do you think the solution set is? It is not no solution, because I'm pretty sure if I picked a number over here, like 6, is 6 greater than -2? Sure it is. Is it also greater than 5? Yes. So to be an and situation like this, we saw one of these earlier where it was an or, and both of them could have worked. You can be here or here. No one cares. When it's an or, it's like, who cares? You be wherever you want. But when it's an and both multiple things have to be true at the same time, the only solution to this problem, if it was an and situation, would be all x's that are greater than or equal to 5 only. You have to be in this purple region to make both of the and parts happy. And if I keep talking, then I'm going to make this worse. So what we're going to do is we're going to work on assignment 23. There's all sorts of possible things that can happen, but I'm telling you, just have faith, do what we've been doing, find your boundaries, test your regions, and then at the end, the key is to ask yourself, was the original problem an and or an or? That's going to be the kicker that sometimes helps you decide what to graph, like, or how to state your solution. Okay. This will be a challenging assignment. So that is that. I'll leave this going. I'll just pause it.